security policy that has been developed for GreenPace was needed due to the nature of our company's use of web-based information systems. This policy will be used to support the defense in-depth best practice by specifying the responsibilities of software engineers specifically in the overall defense. As you can see in the slide, there are many layers of the defense that will not be discussed in detail today, since there is such a wide range of critical components such as physical security, network security, and so on. In the threat matrix here, you can see some of the coding standards that we'll discuss shortly and how they are prioritized in both likelihood and severity. You can see that our highest priority threats are to prevent SQL injection, integer conversion exceptions, and to make sure that allocated memory is freed when it goes out of scope. Many of the items in this threat matrix may be possible to detect with a static analyzer tool such as ReSharper. By letting ReSharper check our code before committing, we have an automated way to reduce the burden on the individual developer to identify some of these issues. The 10 core security principles for GreenPace are validate input data. This is covered by the integer overflows, string correction, SQL injection, and the don't use assertions to validate input. The next is the heat compiler warnings. This is covered by integer conversions and integer overflows. Next, we'll architect and design for security. In doing so, we'll handle all exceptions. Next, we'll keep it simple. To do that, we'll make sure that bitwise and Boolean operators are kept separate from one another and no floats in loop counters. Another core security principle is to default deny. Apply the principle of least privilege. Sanitize data that we send out. To do that, we'll also apply string correctness. Next, defense in depth. And then we'll have an effective quality assurance and secure coding standard. The following coding standards are courtesy of Carnegie Mellon University unless otherwise specified. Integer conversions should guarantee not to result in loss or misinterpreted data. Signed integer overflows. Since an overflow is undefined behavior, it may react differently on different systems and should be prevented. For string correctness, we ensure string buffers are large enough to hold assigned strings, otherwise a buffer overflow could occur. To prevent SQL injection, we'll have user input sanitation and validation. This is typically implemented as parameterized queries and stored procedures. Don't access freed memory. To do this, we'll use null checks, and remember, anything that can be null will be null. We'll have no input validation assertions. Assertions are for test code, so they shouldn't be used to validate input. Our code will handle all exceptions. If an exception can be thrown, then it should be handled by the application. Bitwise and Boolean operators, these don't mix well because they look very familiar, so to reduce the chance of confusion, don't have them in the same statement. Allocated memory should be freed to prevent memory leaks. There should be no floats in loop counters, as that will result in unexpected behavior. Data at rest is when it's being stored in a system such as a database. The policy of encryption at rest means that when data is written to storage media, it is encrypted as part of the database transaction. Data at rest must be encrypted, always in production, and data in lower environments should be adequately redacted to not compromise production data. Data in flight is when it is being transmitted from system to system or within a single system. An example of data in flight is a request made on a web page. The request data is in flight as it is transmitted through the internet to the application. Data in flight should be encrypted using TLS 1.2 or higher in all testing environments and in production, but it is acceptable for local testing to be done in the clear if the request stays within company networks. Data in use is when data is actively being processed by a system. Where possible, data should be encrypted during processing. This also applies to parts of that record that are needed later on in the process, but are not being processed at that time. Authentication proves that the user is who they say they are. Log in via username and password with multi-factor authentication is an acceptable form of authentication for company systems. Authorization determines what resources and what permissions on those resources an authenticated user has. The authorization policy is that each user and service should have the minimum user level of access required to accomplish their task, and that permission should fail closed. The policy always applies to all users. Only specific authorized users are granted write access or the ability to apply changes to the database. And admin credentials are required for the addition of new users. Accounting is the practice of counting API usage for a particular auth token to appropriately bill the user of the system. The accounting policy applies mainly to users who are on an API usage billing schedule. It is also useful as a diagnostic tool, but primarily applies to billing. For users who have a billing plan based on files accessed by the users, a count of those access requests are logged and provided to the accounting department. Begin talking about unit testing. First test we'll go over is the @ should throw out of range exception when index is out of bounds test. This test asserts that an out of range exception will be thrown when the @ method tries to access an index that does not exist. The add entries function is a helper method that calls the pushback method with a random integer under 100 the specified number of times. We'll see that add entries helper method throughout the remainder of the unit test. The assert throws assertion is used to ensure the correct error is thrown. Empty should return false when the collection is not empty. With this test as well, 5 entries are added to the collection, and then the collection empty method is called and asserted that it returns false. empty should return true when the collection is empty. In this case, the helper method is not called to add items to the collection, and the assertion that the collection is empty should be true. Reserve should increase capacity but not size. The reserve method, when called with the value of 7, should increase the capacity of the collection to 7, but the size of the collection should remain at 5. So in this test, 5 entries are added to the collection, and then the reserve method is called with the value of 7. Then with the assertions, it is asserted that the values size t of 5 is equal to the collection size, and that 7 is the collection capacity. Popback should remove the last index. In this test, 5 entries are added, and then an additional test entry is added with a specific value of 1492. After calling the popback function, then we assert that 1492 is not at the final index in the collection. We do this by subtracting 1 from the size of the collection and then calling the at method to get that value. The next test is that pushback should add the value to the last index. In this test, we call the pushback method with the value 1492, and then assert that the value at that index is equal to 1492. The automations that we have in place during the DevSecOps pipeline are as follows. During the assess and plan and design phases, we use automated tools to determine if any third-party libraries in use or projected to be in use have vulnerabilities. That information is used to develop a plan. During the build and verify and test phases, static analyzers are used to assist developers in writing code that meets the coding standards. As we transition to the production phases, we have health check endpoints on each service to ensure that the called service is running and healthy. To monitor and detect, we use application insights to check for anomalies in production applications and to report issues if they occur. For situations like a denial of service or a distributed denial of service attack during the respond phase, we have an automated system such as Cloudflare that automatically rejects requests meant to impair service performance. From there, all we need to do manually is maintain and stabilize the system. Specific tools we use are Visual Studio for our integrated development environment, which has many built-in features and static analyzers to help in developing secure code. In addition, we also utilize the ReSharper plugin for C++ in order to take the static analysis to a higher level. For unit testing, we currently use XUnit. In our CI/CD pipelines, we use Azure pipelines to test and deploy the builds. Finally, once the solution has been deployed, we have application insights set up on all environments to monitor services and provide detailed logging. Some of the risks that we are aware of with this current policy are that we may have an over-reliance on static analyzers. This is something that developers should be aware of and not fall into a false sense of security. Another risk is the high amount of system complexity. This is just part of being a wildly successful software company like GreenPace. We have many features to support, and the system required to do so is complex. We always need to be on the lookout for ways to simplify, so this is something to bear in mind. For our benefits, we have an excellent code review process. Since we are aware that over-reliance on static analyzers could become an issue, we require 2 approvals on all code that is merged with the master branch. Another benefit of the system is our layered defense. This layered defense does not rely on any one piece of the system to perform all security functions. If an attacker were to break past one layer, they would be met with just another layer of security. I have 2 recommendations for the next iteration of this policy. First, CI/CD integration testing. With integration testing done in the pipeline, that removes the bulk of any need to complete manual testing before deployments. Manual testing is dangerous because things can easily be missed and issues can go into production without warning. Next, I recommend implementation of a test-driven development workflow. Writing tests first and only writing enough production code to make the test pass ensures that you have full code coverage in unit tests and the tests are actually checking for what the code needs to be doing. My conclusions are, first, that security is everyone's responsibility. Each of us has expertise and slightly different experience that may help us recognize different issues in different situations to make sure vulnerabilities are caught. That leads to my next point. If you see something, say something. Don't assume that someone else has seen it because it was such an obvious error to you. Let the person know, with humility of course, and we'll get those issues fixed together. That brings me to my last point. We're all on the same team. Everyone on the team did the best they could with the information they had at the time, so there is only reason to be encouraging to team members and to point out the flaws in our own and others' work to make everyone better. Here are my references. Please like and subscribe. Remember to hit that bell thingy and let me know in the comments if you have any questions. Thanks.